In the last lecture on stoichiometry, I had solved some problems. Some 2 problems were left. So, I am projecting those problems again and I will solve these problems also. So, although these problems are there in lecture 1, but I thought maybe I will repeat. So, this problem 7 is about the aluminum which is produced by electrolytic decomposition of Al2O3 using a carbon anode, and what you have to calculate the chemical reaction occurring balanced with minimum whole numbers. You are not required to round off, but you have to find a chemical reaction with minimum whole numbers and kg of Al2O3 consumed and cubic meter of CO and CO2. The next problem which we have to do is about the reduction of zinc oxide by carbon, and some of the conditions are given of the reduction, say 1/5 of the ZNO remains unreduced and so on. So, you are required to calculate volume of CO, weight of CO, volume of CO2 and so on. So, I will be solving these problems, so that this lecture on stoichiometry completes. So, the solution of problem 7, for example, says that I will write moles of aluminum produced, moles of aluminum produced, that will be how much, can you tell? That will be 300 divided by molecular weight of aluminum. I have taken here 27, that is equal to 100 by 9 kg moles, which is also equal to 50 by 9 kg moles of alumina. Because in Al2O3 there are 2 moles of aluminum, that is very simple. So, if I write down now the equation, say 50 upon 9 Al2O3 plus x mole of carbon, because x is to be determined, that is equal to 100 by 9 moles of aluminum plus 150 upon 9 into 0.85 CO as per the statement of the problem, plus 75 upon 9 into 0.15 CO2. Now, this equation I have written as per the statement of the problem, that says 85% of the oxygen forms CO and 15% forms CO2. So, from here one can find out x, that will come out to be equal to 138.759, and rest of the exercise I leave on you to find out the balanced chemical equation with whole numbers. I am writing the answer, which is, say, the balanced chemical equation with whole numbers. Mind you, you are not required to round off. The equation is now 40 Al2O3 plus 1 moles of carbon, that is equal to 80 moles of aluminum plus 102 moles of carbon monoxide plus 9 moles of carbon dioxide. Say, this is the answer for part 1. Answer, this is for 1, that is a balanced chemical equation. Now, for second straightway we have to find out the kilogram Al2O3, that is straightforward from the balance equation. So, kilogram Al2O3 used, the answer would be 566.7 kilogram. That is the answer for 2. For 3, that is the volume of CO. Now, once you have the balanced chemical equation, then everything follows on its own. 317.3 meter cube and volume of CO2, that is equal to 28.0 meter cube. Mind you, these volumes are at 1 atmospheric pressure and 273 Kelvin. You always make a habit that whenever you report the volume of the gases, please mention pressure and temperature. Without mentioning of both, the expression of volume has no meaning at all. So, this is the answer solution for question number 7. Now, let us take the question number 8. Now, question 8, again if you follow the way the question is there and the conditions under which zinc is produced, again say you start, I will give you a brief solution. Say you start with the moles of zinc, that will be equal to 100 into 50 upon 100 into 1 upon 65. Say here molecular weight of zinc I took 65. So, I will be getting here 0.77 kg moles. Now, the problem says 1/5 of the ZNO remains unreduced. So, moles of ZNO reacting. Now, mind you, 1 mole of Zn is also 1 mole of ZNO. So, 0.77 kg moles of Zn, that equals to 0.77 moles of ZNO also. So, moles of ZNO reacting will be 80% of this, that is 0.62. Now, straight away one can find out the answer. So, I am writing down the answer for you. Answer for 1, that is moles of CO, that is equal to 0.62. This is equal to 13.89 meter cube at 1 atmosphere and 273 Kelvin. The problem says you have to find out at 273 Kelvin and 760 millimeter of mercury, and also problem says that you have to find out at 300 degree Celsius also. So, that will also be equal to 13.89 into 760 upon 750 into 573 upon 273. So, that is equal to 29.54. This is meter cube at 750 millimeter mercury and 573 Kelvin. This is the answer for question 1. Weight of CO, straight away you can find out 17.36 kg. You have to multiply it by the molecular weight of CO. Third, volume of CO2, straight away you can find out. You have to find out volume of CO2 formed at 750 degree Celsius and 770 millimeter pressure due to burning of CO. So, I am straight away I will write down the answer, you find out yourself, that is 51.37 meter cube at 770 millimeter mercury and 1023 Kelvin. So, for 3, and the answer for question 4, the volume and weight of air used in burning the CO. So, volume of air volume of air that is equal to 33.06 meter cube expressed at 180 m and 273 Kelvin, whereas the weight of air here I am writing down, weight of air you multiply by its molecular weight 42.80 kg. So, with the solution of both these problems, the lecture on stoichiometry ends, and today I will again be starting with a fresh topic, that is the thermochemistry, an introduction to thermochemistry. Now, you know, whenever you want to perform the heat balance of a process, you require to do at a steady state heat input that is equal to heat output. So, you do require to calculate the heat effects produced by the chemical reactions. In fact, the chemical reactions are often accompanied by either liberation of heat or absorption of heat. Now, for example, 2Fe plus 3O that gives Fe2O3 and liberates heat of the order of 198,000 kilocalorie. Similarly, another example, C plus O2 that is equal to CO2 and liberates heat of the order of 97,200 kilocalorie. Now, these heat effects are very important when you want to analyze the energy balance of a process, because you must know what reactions are producing heat, how to calculate the heat of the reaction from a temperature of T1 to a temperature of T2. For all these purposes, the first law of thermodynamics it concerns with energy changes within the system, Now, I am not going into the detail of the first law of thermodynamics. I will be giving you only that particular portion of first law of thermodynamics which is relevant for heat balance calculation. So, the first law of thermodynamics states that change in internal energy, that is E2 minus E1, that is equal to Q minus W. I think all of you know, where E2 and E1 are energy contents that is internal energy of the system, in state 1 and state 2. I must mention here that thermodynamics deals with the initial and final states only, not in between. That point is to be clear. Q here is heat absorbed by the system, by the system. Of course, from the surrounding, whereas W, that is equal to work done by the system on the surrounding. By the system on the surroundings. This is a very simple, and you must have read very often in your undergraduate course on thermodynamics. Now, heat content or enthalpy of a system is a thermodynamic property to which we are concerned. So, this heat content or enthalpy, which is thermodynamic property H, that is equal to E plus P V, where P, that is equal to total pressure, and V, that is equal to total volume. Let me call this equation as number 2. Now, by 1 and 2, by equation 1 and 2, we get H 2 minus H 1, that we are considering system is in a initial state 1 and final state 2. So, H 2 minus H 1, that is equal to Q minus W plus P into V 2 minus V 1. Let us consider this equation number 3. Now, if work done by the system, by the system on surrounding let us say it is work of expansion. Surrounding is work of expansion, that is only expansion work is done. Work of expansion. So, in this case W, that equals to integral of 1 to 2 P dV, and that is equal to V 2 minus V 1 into P. Let us call this equation number 4. So, by 3 and 4 we get a very important relationship. By equation 3 and 4 we get delta H, that is equal to H 2 minus H 1, that is equal to Q, and this is a very important relation, because this suggests that heat absorbed by the system can be determined in terms of its enthalpy in the initial state as well as in the final state. And remember that enthalpy is also a state property. Now, this particular equation is valid when the change from state 1 to state 2, it occurs by a path of constant pressure in which only expansion work is done on the surrounding. That means, this is valid for an isobaric process. For an isobaric process, that means taking place at constant pressure, delta H is equal to Q, and also the Q is the heat absorbed, and heat absorbed by the system can be related to the change in enthalpy or the heat content, and enthalpy is also a state property of the system. Now, say if in isobaric process, if an isobaric process involves work other than expansion then in that case delta H that will be equal to Q minus W dash. Now, that is an important thing here, because delta H is equal to Q is only valid for an isobaric process, which involves only work of expansion. But if there is other work of expansion, for example, in electric furnace, electric is supplied or electricity is supplied. So, in that case, the electric process at constant pressure, this minus W equals to the input of electrical work to the system. So, that is important. So, I will write for you, say W dash, that is equal to work done by the system on the surrounding in the constant pressure process, important is other than expansion work. So, as I have just now given an example, in an electric furnace which also operates at constant pressure. So, minus W means that much amount of electricity has to be supplied into the system. Now, most metallurgical processes, they follow a path of constant pressure, that is, in various metal extraction and refining, hardly the pressure is rather varies. So, most of the processes they occur at constant pressure. So, in that case, the heat effect for a process Q p can be related or relates very well to the property of the system, that is enthalpy. So, that is an important conclusion. That means, the change in heat content depends only on the initial and final state and not on the path taken by the process. So, that is an important conclusion from the first law of thermodynamics, which forms the basis of calculation for various heat effects while performing the heat balance of a particular process. This is a very brief introduction of first law of thermodynamics. The details you can go through in any book on thermodynamics to clear the concepts of enthalpy. But what is important over here is that because most metallurgical processes they occur at constant pressure, therefore, the enthalpy can be very well used in order to find out the heat content. That is where the important thing over here. Now, let us see various heat effects. What are the various heat effects? Various heat effects. Various heat effects. First, the changes due to change in temperature in pure substance. Change in temperature of, or rather in pure substance. Now, clearly a substance contains heat by virtue of its temperature. When a material has certain temperature, it has certain amount of heat. What is important is the change in heat due to change in temperature, that is what we require. Now, this is calculated by taking a basis. Now, the universally accepted reference temperature, the universally accepted reference temperature, I hope you must be knowing from your elementary course on thermodynamics, is 25 degree Celsius or 298 Kelvin, because the enthalpy at 298 Kelvin or 25 degree Celsius is taken equal to 0. Therefore, the change in heat content is defined with reference to the enthalpy content at 25 degree Celsius. Now, say heat content of most of the inorganic materials, whether elements or compounds, you can find out in any standard thermodynamic book. Various books they give the values of heat content due to change in temperature in terms of H T, that is the enthalpy at temperature T, minus H 298, that is the change in heat content when a material is heated from 298 Kelvin to a temperature T Kelvin. So, the values are listed in the table by using the following formula, that is H T minus H 298, that is equal to A T plus B T square plus C T to the power minus 1 plus D, and the units are kilocalorie per kg mole, which is also equal to calorie per mole, or sometimes you may find it is also written in kilojoule per kg mole, that is also equal to joule per mole, and in FPS system it is also given in the respective units. So, that is one important thing, that the change in heat content of any material can be determined from seeing this particular table. Another heat effect is that the change in heat content due to changes in state of aggregation, in pure substances. Now, for example, melting, vaporization. Do you know still another change? Can you get it? That is the allotropic transformation. In iron carbon system, iron changes from alpha to gamma to delta. So, accordingly the heat evolved or heat will be absorbed, that depends on the system under consideration. Now, here the changes which occur, it occurs at a constant temperature, that point is important. No change in temperature occurs due to change in the state of aggregation. So, that is commonly called or the latent heats. Sometimes you also call heat of fusion, so latent heat of melting, latent heat of vaporization, and the heat evolved or absorbed during the allotropic transformation. This is also very important, because when you calculate, say if you want to calculate the heat content in, for example, a pure material from 25 degree Kelvin to a temperature T, then you must see what changes are occurring during its variation of temperature from 25 to that particular temperature. If you have to take into account all these changes which are occurring to calculate the heat content, that is an important. C part is that, say, changes in heat content, changes in heat content due to chemical reactions in the system, due to chemical reactions in the system. Because if a chemical reaction occurs, then heat may be evolved or heat may be absorbed, and that you have to calculate. Now, in order to calculate the heat content due to chemical reaction, one has to proceed with the data on the heat of formation of compounds. Now, this heat of formation of compound that are also listed in any standard book of thermodynamics. So, that is also to be noted while finding out the heat of formation of the compound. Now, for example, if you take a reaction, say Fe2O3 solid plus 3C solid, that is equal to 2Fe solid plus 3CO gas, you are required to find out the heat of this particular chemical reaction. Now, you can find out the heat of this reaction from the heat of formation of the compounds. I am giving you the heat of formation of compound, say delta HF CO, that is equal to minus 29,160 kilocalorie per kg mole. Mind you, this value is at 298 Kelvin. Similarly, delta HF Fe2O3, that is equal to minus 198,500 kilocalorie per kg mole. This is also at 298 Kelvin. Now, you must note that the tabulated values or all the thermodynamic tabulated values, they are listed at 298 Kelvin temperature. That is an important thing. So, now the heat of formation of the pure element is 0. That is the thing you have to know it. So, now delta HR, that is heat of reaction at 298, that will be equal to 3 delta HFCO, that is heat of formation product minus heat of formation of the reactant, minus delta HF Fe2O3. Now, what I have to do is very simple. Now, I have to substitute the value of delta HFCO, which is 29,160, and Fe2O3, I have to do multiplication and subtraction or whatever you want to do it. So, the answer would be plus 111,020 kilocalorie. Now, this reaction is highly endothermic. Now, this Fe2O3, this reaction will have 111020 kilocalorie, Now, you can say per kg mole of Fe2O3 or per kg mole of carbon or per kg mole of iron, whichever way you want to say. So, that is what the calculation on the heat of reaction. Now, let me take another example. Let us take it now, say Fe2O3 plus 3 CO, that is equal to 2 Fe plus 3 CO2. All the values I have given. Now, I am giving also here delta HF CO2, which is not given above, 298, that is equal to minus 97,200 kilocalorie. Now, if I forget somewhere to write 298, I mean tabulated values, they are always at 298 Kelvin. So, there should be no confusion. So, now I can calculate delta H naught R for this reaction. Delta H naught normally refers at 298 Kelvin. So, that will be equal to 3 into delta H F CO2 minus delta H F Fe2O3 plus 3 into delta H F CO. However, if in this equation you also write down the state, say this is the solid, this is gas, this is solid, this is gas, this will also help you. For example, in some reaction the product, one of the product is liquid, then you have to take the latent heat of fusion also in calculating the heat of content. Therefore, it is advisable in the beginning to calculate the heat of reaction from the heat of formation of the compound, to write down the equation by mentioning the state also in the parenthesis. That is important thing here. So, if you just substitute the values, then you will be getting minus 5,620 kilocalorie. Now, remember this equation, this reaction now is exothermic. So, that is how you will be calculating the so called heat of reaction at 298 Kelvin. Now, the heat of reaction also depend on the reaction temperature. So, I will write down heat of reaction also depends on temperature. It is temperature of the reactants as well as temperature of the product. So, the Kirchhoff's law, I think you must have read, is used. So, heat of reaction, say delta H R at any temperature T 2, that will be equal to say delta H R at 298 Kelvin plus H T 2 minus H 298 products minus H T 2 minus H 298 reactants. That is how you have to find out the heat of reaction at any temperature. Now, let me illustrate by an example. Now, let us calculate heat of the following reaction, heat of the reaction mentioned below at 1500 Kelvin. Now, the reaction is ZnO S plus Cs, that is equal to Zn gaseous plus CO gaseous. Now, mind you, in this reaction it is very important to write down the state of the reactant and product in the parenthesis, because you note that in this reaction the reactants are in the solid, whereas the products they are in the gaseous state. Zinc is also in the gaseous state. So, while calculating the heat of reaction, you have to consider the state of transformation of solid zinc to gaseous zinc via liquid. So, that thing is important. For that purpose, in thermodynamics it is always advisable to write a chemical reaction by putting the state of substance in the parenthesis. So, now all that we need the value of heat contents. I am giving heat contents H 1500 minus H 298 for ZNO solid, that is equal to 14800 kilocalorie per kg mole. For carbon, H 1500 minus H 298 is carbon which is solid, that is equal to 9291 kilocalorie per kg mole. So, H 1500 minus H 298 zinc gaseous state, that is equal to 37,150 kilocalorie per kg mole. Similarly, last one H 1500 minus H 298 for CO gaseous state, that is equal to 5480 kilocalorie kg mole to the power minus 1. So, that is what the various values are given. Now, also you require to calculate the heat of reaction. Say you require the heat of formation of compound, say delta HF ZNO, that is equal to minus 83,310 kilocalorie per kg mole. Delta HFCO in the gaseous, this is the solid, that is equal to minus 29,160 kilocalorie per kg mole. So, you see, in calculating the heat effects, you have to collect a large number of values, and it is very important that you collect the right values in the right state. That is an important. Now, say first we have to calculate delta HR 298. So, delta HR 298, that as I already illustrated in the previous example, product minus reactant, heat of formation of product minus heat of formation of reactant. I am writing straight away the answer, that is 54,150, mind you this is plus kilocalorie per kg mole. Now, this is heat of reaction at, this is the heat of chemical reaction at 298. Now, at 1500 degree Celsius. So, what we have to do now, say delta HR, delta HR 298 Kelvin plus sigma H 1500 minus H 298 product minus H 1500 minus H 298 reactant. Now, the values are already given, so I am straightway substituting the values 54,150 plus 37,150 plus 5480 minus 14,800 plus 9291. So, if I solve, you will be getting 72,689 kilocalorie per kg mole. Kilocalorie per kg mole. Now, suppose if you want to calculate kilocalorie per kg of zinc, then what you will do? You will divide this value by the molecular weight of zinc. If you require to calculate kilocalorie per kg of ZnO, then you have to divide by the molecular weight of ZnO. So, that is what kilocalorie per kg mole it means. Now, this is how you will. Now, I will give you another example. Say for example, calculate delta H R at 1500 at 1200 Kelvin for the reaction Fe2O3 plus 3CO, that is equal to 2Fe plus 3CO2. In earlier problem, we have calculated for this reaction delta HR 298, that was minus 5620. So, I straight away put down the value delta HR at 298, that we calculated in earlier problem minus 5620. Now, you need certain values. So, I have to give you certain values, say H 1200 minus H 298 you need for iron, you need say H 1200 minus H 298 for CO2, you also need H 1200 minus H 298 for carbon monoxide, H 1200 minus H 298 for Fe2O3. So, let me give you these values, that is this is equal to 8370. The units I am writing at the top, kilocalorie per kg mole. For CO2, 10,650, this is 6,798, this is 30,870. Now, once these values are given, then it is simply addition and subtraction. So, delta HR at 1200 Kelvin for this reaction, I am straight away writing down, that will be equal to minus 8194 kilocalorie per kg mole. So, this will be the answer for this. So, that is the way you will be calculating. Now, I give you further more exercises. So, you do it, say find heat of reaction of the following chemical reaction at 1400 Kelvin. Just for your practice, C solid plus O2 gaseous, CO2 gaseous, this is for this find out, Also find out for this reaction CO2 gaseous plus C solid 2CO gaseous. Also find out ZNO solid plus CO gas, that is equal to Zn gas plus CO2 gas. Collect the values from thermodynamics and find out this thing. Now, this is one way of finding out the heat content, where straight away you are given with the value of H P minus H 298, because so these values are tabulated and somebody has worked for you, so that you do not need to do a lot of calculation, but the tabulated values are at a particular temperatures. Suppose you want to calculate the heat content in between temperatures, suppose tabulated values is 1400 Kelvin and 1500 Kelvin, you want to calculate the heat content at 1450 Kelvin, what will you do? So, for that the heat content can also be determined by specific heat values of the elements and compounds. You know, so the specific heats of elements and compounds can be used to calculate heat content, because here you are not restricted with the temperature that is given in the table. The table does not give the values of all temperatures, it starts 200, 400, 800, 900. You want to calculate in between, what will you do? For that you can use the value of Cp. Now, the specific heat of a substance, it also varies with the temperature, you know, that is the Cp, that is equal to A plus Bt plus Ct to the power minus 2, where A, B, C are constant. Also in some books written plus D. Well, the D value is so small, if you can neglect, it does not matter much. So, normally Cp is equal to A plus Bt plus Ct minus 2 is used for calculation of heat content at any temperature. However, for the sake of convenience, one may take Cp is equal to A plus Bt also. You must note that the calculated values will not be accurate. If you are looking for accurate and correct calculation, then you have to use the Cp, that is equal to A plus Bt plus Ct to the power minus 2. A, B, C are constant, and these values of Cp, they are listed for most of the elements and compound of interest in metallurgy in any thermodynamic book. So, from that value one can determine the heat content value, and in the next lecture I will give you an example how to calculate the heat content from using the Cp values. Till then, enjoy.